Good morning, everyone. Welcome to another episode of Sound Talk Show. So today I'm going to code Wolfram language Mathematica, and I'm going to code this hyperboloid of one sheet. So I'm actually going to generate this image, okay, the rotation of a bar, and possibly also this one, and the silhouette of a cube when you spin it like a dice. Here's a photo. Is a hyperboloid. Is that figure? Okay, so this is what we are going to do. And here is an interesting 3D printed toy you can make. Someone else made it. This curve is interesting because it's made of one line. That is, it can be generated by simply rotating a single line. Such a surface is called the rule surface. Mathematically, you say for every point on a curve, on the surface, there is a line on the surface passing through it for each and every point on the curve. And there are a lot of architectures, towers, using this concepts, very popular in architecture. So this is called ruled surface, and this happens also to be one of the conic section surfaces. That is, the cross section of this surface. If you cut it, horizontally, then it's going to be a circle. If you cut it vertically, then it's a parabola. It's a surface of revolution of a parabola. So there are several ways to generate this curve. You can rotate a parabola around one of the axes and form this surface, or you can simply rotate a line. So this is very interesting. This is fascinating because there's a whole family of these similar things. For example, this surface is a hyperbolic paraboloid. It's also made of one single line. Okay, so we are going to code this today. Let's start coding. Okay, good morning, everyone. If you are here, say hi. Okay, comment and comment and ask me questions. Okay, let's code it. So first of all, what we need to do is to generate a tube. Okay, so let's go to Mathematica. And by the way, let me show you this one. Okay, Hilbert Curve, fantastic, beautiful. Okay, so you generate this by this command, Hilbert Curve. Okay, so let me show you Hilbert Curve. Let's magnify. Hold on a second. Magnify 200 and remove that. Let's say 1. Okay, so you got that. Then if you say 2, you got that. If you say 3, you got that. If you say 4, you got that. So you got the idea. It's a recursive. It's a space feeding curve. It's called space feeding curve because this is a shocking discovery in mathematics about 200 years ago. Because when you see this is a single line, let me show you a table. Okay, let me show you a table n. Then okay, so a table of this expression, then n goes from 1 to 7. Okay, so let's do that. So you can see a progressively more complex curve. It's using a simple rule. From one line becomes that, and you apply this rule for each line segment again, and it becomes that and that. So eventually, if you go infinite number of steps, it will fill out the plane. So what's interesting? Well, first of all, it's artistically, it's extremely interesting. Okay, this is a beautiful thing. For example, let's copy that. Let's paste it here, and let's magnify. This is fantastic. You can use this for a background. Okay, for website background or your desktop background. Actually, I might do that. And but mathematically, it's also very interesting because a line, originally, you have a line is a one-dimensional curve. But now if you have this thing, infinite number of steps, so is that it can be proven that this actually fills out the square completely. So the question is then, is this a thing, how do you define your dimension? Is it two-dimensional or one dimension? Then later on, you started to have the idea of fractal dimensions, okay? So anyway, that's digression. I'm gonna do this, I'm gonna code on that now. Let's see the pop-up window. Hey, Ronnie. Okay, let's code this thing, okay? So let's go to Wolfram language, close that. Let's code this thing. Okay, let's start here. So first of all, so how do you do this? So first of all, you want a tube. Okay, let's get the pen. So you want a tube. Okay, first of all, you want to rotate the tube. I mean, make a copy of the tube and rotate it. Make a cylinder. Okay, before we actually tilt the tube. So let's do that. So tube in Wolfram language, it's a built-in graphics primitive. Okay, so you can see, so here is a tube. Okay, so tube, you got, say, let's see. Okay, so let's see start and end. Okay, so hold on a second. So let's see start point. Start point equals to, so we want to give it a point. This point will be 3 numbers. This will be, let's say, now let's not say start point, let's say length. Okay, len equals to 2. Okay, then we want to, how do you do this? Let's do it the easy way. Okay, let's forget about elegance. Let's just do the easy way. So you want start point. Okay, start point equals to 3 numbers. Are tubes a built-in feature in the language? Yes, it's a built-in graphics primitive. For example, to show a tube, this is all you have to do. That's all you have to do. So you just say graphics 3D, then tube. Tube takes 2 arguments. The first argument is 2 points, beginning and end position of the tube. Then the coordinates. Then the second argument is the thickness. Is it? Yes, the thickness of the tube. Okay, so as simple as that. So okay, so we want to do, so first of all, a tube, 2 points, start and end, start point. Okay, start point will be, let's say 0, 0, -1. Okay, and let's say end point, and let's say 0, 0, 1. Okay, actually, so length, so let's do it this way. Yeah, so I discovered, why don't we do this? So we got start point, we got end point. Now let's evaluate it. Let's just try it. Okay, then graphics 3D, that's a wrapper. Whatever inside should be graphics primitives. So graphic primitives are like points, line, a rectangle, a cube, polyhedron, anything, So inside this will be a tube, and Okay, start point, end point. Okay. Okay, we got a problem. Oh yeah, so start point, end point, they need to be inside a curved bracket. There we have it. So we got a tube centered around the origin, going up and down 1 unit. Okay. Yeah. Okay. So you see. So then we need to okay. So once we have it, we want to rotate the tube. Okay. Okay. You see, our goal is to generate this. So before we rotate, let's translate. Let's move the tube to the side, then make a copy so it goes one round. Okay. So what we want to, in order to move, there is a built-in function called translate transform. Okay. Let's see, translate. Okay, let's look at the documentation. Translate string. Attempt to translate a string into the specified okay, that's not okay. That's English translate. We want the mathematical translate. Oh, wait. Actually, we got transliterate. So actually what we want is translate. Okay, let's look up the documentation. Translate GXY. So G is a graphics primitive. Translate by a vector. Okay, so now let's define another variable, offset. Let's say girth. Girth equals to girth radius. Okay, equals to, let's say 1. Okay. So evaluate that girth radius. So now we want to translate this thing, translate this tube thing by girth radius. Okay, that is done, and let's slap on a graphics 3D so it actually shows it. Okay, we got an error. Oh yeah, we forgot to translate girth radius. Okay, hold on a second. Translate girth radius. This needs to be a point. So a point, that would be 0, 0. Yeah, 0, 0 girth radius. Let's do it. Fantastic. Now, what's the difference between these two? Well, let me show you. You'll see if I show the let me show you this. Okay, graphics 3D. Okay, that's the graphics wrapper, and here we want to specify options. We want to show axis. Okay, axis true. So we can actually see the ticks. Okay, now put the whole thing inside. Okay, run it. So now you can see the axis. So 0, 0, 0, 0. Wait, did it translate? It didn't translate. 0, 0, 0, 0. 1, 2, 1, 2. So, okay. So let's change the length to 1. Okay, then let's also put axis true here. Let's add another variable, 1 tube equals to that. Okay. So we don't have to type the whole thing. Okay, so you forgot to evaluate 1 tube. Now we did evaluate. So now we got the tube. Okay, so so check the coordinate 0, 0, 0, 0. So x, y, and 0, 0, and z is 1 unit in each direction. Okay, so far so good. Now let's try the translate thing. Is that right? Translate. Okay, translate one tube by 0, 0 girth radius. RADIU radius. Okay, yeah, okay, so let's get the spelling correct. Radius, not radio. Okay, so what is going on? So that's 0, 0. That's again 0, 0. It did not translate. Translate graphic represent, okay, translate graphic primitive represent a multiple copy of G translated by a collection of vectors, okay? So here is an example, translate circle from 0, 0 to 1, 0. Yeah, so that works. And here is a sphere translated by, oh, I see. So the vertical axis, yeah. So actually we moved it up by this much, by girth radius unit. That's a mistake. It should be x, okay? So girth radius, yeah. So do it. Now you can see, you see the x-axis is 1. So we have moved this vertical bar to the x-axis, 1 unit, okay? Now we want to rotate it. Okay, wait, before we rotate it, let's, okay, how do you do that? You want to rotate, yeah, let's rotate this thing around the center. And every time we rotate, we make a copy. So eventually we have a kind of a cylinder. Okay, so there is a function for that, rotate. Okay, let's look at the documentation. Rotate graphics primitive given an angle. Okay, so how do you want to rotate? So this is a three-dimensional thing. You want to rotate it around the origin and around the axis, z-axis. Okay, so rotate about the point x, y. So rotate. Okay, so that's a 2D case. Rotate about the point x, y. So this is a 2D case. So this is a 3D case. Rotate. The first argument is a graphic primitive, whatever graphics. Then the second argument is two vectors, a pair of vectors. Each vector is a maybe 2D or 3D. So it transforms the vector from, the first vector to the second vector. So that's right. Okay, so we can do that. Now let's forget about elegance. Let's just get this to work for now, okay? So so we want to rotate and translate. So what are the other ways? So rotate 3D graphics primitives by theta radians around 3D vector W anchored at the origin. Okay, this is the form we like better. So okay, let's do that. So copy the above code. We first of all translate it. Okay, we translate it there, that's the code, but now we want to rotate it. Okay, rotate this thing by how many degrees? 30 degrees, okay? Let's say 30 degrees. Okay, we rotate it by 30 degrees, and around what axis? Around the vector 0, 0, 1, okay? So let's see if that works. Okay, so now let's check the coordinate. Now let's look from the top down. Okay, it's hard to see. It's hard to see. So if we rotate it by, let's say, 45 degrees. Yep, you can see we are looking at from the top, and the bottom axis is x-axis, and the vertical axis is y here, and you can see what? Shit. And you can see, you see this thing is not, you know, it should originally it should be one over here and one over there. It should be there, but because we rotate it, it should be somewhere. Yeah, one here. You see here one, and you see here one. So it should be here. Now because we, you know, on the lower left is the origin, so we rotate it. So this looks correct. So we can, let me show you with technology. So you can see if we look at this as an wait, this should be a curve, right? Okay. Wait, this is a bad drawing. Okay, so delete. So this is the origin. This is 1, and that is 1. But anyways, it's something like that. Okay, we rotated it. To know for sure, we can just make a table of it, like make many copy of it. Let me show you. Okay, so let's create a table. Let's put the expression inside, paste it here, and here we say n goes from 0 to 360 in steps of 30. Okay, so now we change the 45 degrees to n. Okay, so now we should have several copies. Fantastic! Did you see that? Our scheme is working. Fantastic. One shot coding. Okay, no trial and error. This is the thinking method of coding, the mathematician's way. Well, actually, mathematicians has many different kind of styles. Some of them actually do trial and error. So anyway, so we got this now. So we got this multiple copy. There's one more thing we want. Okay, let's do more. So let's in steps of 10 degrees. So we got the serious thing. So let's actually in steps of 5 degrees. Okay, so we got this fantastic thing. Lots of tubes. This is fantastic. Okay, now let's add some specularity, color. Let's add some coloring. Okay, let's add some fantastic coloring here. Okay, we got this wrong. Oh yeah. This should be inside. What? Yeah. What is the graphics options? What is the error? An improperly formed option head specularity encountered. Okay, this is actually wrong. Okay, let's forget about that. Let's add that later. Okay. Okay, so now let's go to the next step. Now we want to tilt each of the tube a little bit. So we begin here, one tube. Let's rotate this one tube. Okay, yeah. So let's rotate this one tube. Let's put here. Okay, so let's work here. So we want to rotate just like before. Where is it? We want to rotate it, and we want to rotate the one tube here, and by the x-axis. Okay, now by the x-axis 1 0 0, we want to rotate it. So now we want to rotate it by how many degrees? By 10. By a number tilt level. Okay, so let's copy that. Let's modify this one tube code. So we can comment that out. So we need to define a tilt level. Okay, tilt level equals to degree. Okay, tilt level 10 degree. Okay, so we rotate this tube by tilt level 10 degrees around the vertical vector. Okay, let's try that. Oh, what? No, this does not look right. This is rotate by x-axis. This should be three-dimensional. Start point, end point, what's going on? So let's do this. Well, it works. Somehow it prints that. This is it. You know, I was kind of surprised by this printout, because it doesn't make sense. It actually rotated the text, but actually did it work? It seems to work, you see. So actually it worked. Now if we try this, fantastic, we got it. So actually we are complete. We completed what we want. Now all we have to do is just adjust the tilt level. Okay, so let's remove the intermediate steps, You know, so when people look at this, oh my God, this is amazing. How did you do it? So tilt level, it will be, let's say 30 degrees. Do it and do it. Fantastic. Not enough. Let's say tilt level. Wait, why is it not enough? 45. That's wait. So wait. Okay. We got something to fix. Actually, this is not perfect. Okay. So this is not perfect now. The tilting is not correct. Okay. Which way should you tilt? No, the tilting is actually correct, but so let's adjust let's make them one shot. Okay, let's make them one single code. Okay, let's tilt 45 degrees. Let's increase the length 2. Okay, let's see. There it is. Beautiful, fantastic. Too many. Okay, let's number. Okay, number of bars, number of tubes. Okay, let's say 90. Okay, so number of tubes will be how many of them? How many copies of them? So, and all we have to do is adjust this 365 divided by I think so. Okay, number of tubes, let's say 40. Fantastic. Okay, okay, there is we got a problem because a circle's got 360 degrees, not 365. I got confused with number of days in a year, so it's 360. You see this problem? You see these two? So now we fix that. Do it. Fantastic. So here is the whole code. Now we can do something more fancy. Okay, let me show you. So what we are going to do? Yeah. So what are we going to do now is to see what is the effect of the tilt to the overall shape. Okay. So you see, we can make it very, very thin in the middle, like young girl's body. Sexy, you know, but it not too much. Then it becomes a bee. You know, so there's a term for that, wasp waist or something like that. So we can make it the whole thing into one single expression and see their effects by manipulate the whole thing. Okay, so we got, you know, the Wolfram language notebook is not a great editor, so you know, I'd rather code this in Emacs. So you do the whole thing, then let's say D, okay, D from, so tilt level, tilt X from 0 to 45, and in steps of 5, okay? So copy the tilt and replace the tilt by okay, so we gotta do this tilt level. Okay, I think that does that. So let's play. Okay, so let's play back and forth. Can we do that? Yeah. So that is the effect of tier level. Now let's do one more thing. Let's fix the viewpoint so the graphics doesn't jump up and down. So wait, let's save the notebook. Okay, let's fix the viewpoint. Okay, so graphics 3D. Let's just say front. Okay, do it. Okay, it's still, the size changes. Let's fix the size. So viewpoint, let's not say front. Okay, let's magnify. Viewpoint. Let's see, viewpoint, where do you want to view this thing? So X is 5, Y is -5, Z is 5. Okay, let's try that. Okay, and view distance. View angle, viewpoint, view angle, view vector. Plot range. Let me get this to show. So view plot range -5 to 5 for X and Y and Z. Okay, let's do it. Okay, now they look, now let's lower the 3, 4, 4, 4, 4, yeah. Do it. Yeah, plot range is I'm so tired of Wolfram language editor, so let's do this in Emacs. It's much faster. Okay, that's it. That's it for today. 7:44. Thank you for watching. If you like my stuff, donate. Okay, donate by my Emacs tutorial. PayPal me, Patreon me. So that's what we want to do, and we did it. Fantastic. Thank you guys for watching, and next in the coming days, I'm going to also this would be interesting. Now this, and also we can prettify the code. Actually, there's a lot of code to prettify. So maybe let me do this. We can prettify the code because now there's a lot of parameters. We can make it a functional programming into one single line. So right now you see it's using a bunch of variables. You don't have to. You can make them all just one single line. But I'm gonna play offline. Okay, so bye guys.